Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
My experimental discovery was newsworthy and made me the cover story of top mathematics publications. I was the cover story of the June 1990 issue of the Science News, that is the flagship publication of the Society for Industrial and Applied Mathematics. The reason my experimental discovery was cover stories of mathematics publications was that I discovered how to use parallel processing and how to use the technology to solve the toughest problems in calculus. In the old way, we unsuccessfully tried to solve the toughest problems in calculus on the blackboard or motherboard and failed to solve them on one central processing unit. In the new way, we can solve the toughest problems in calculus and solve them across up to 10 binary million central processing units. During those 20 years, onward of June 1970, my mathematical and scientific maturity grew as expected of a mathematical scientist that devoted 20 years to his craft and searching for new calculus at the frontier of abstract calculus and searching for new algebra at the frontier of large-scale algebra and searching for the fastest floating point arithmetical operations at the frontier of the most massively parallel supercomputer ever built, and that is a global network of 64 binary thousand central processing units, and that is an internet. In the 7th year of that 20-year sojourn to the farthest frontier of computing, I drifted and became an astronomer who was primarily interested in distant galaxies in outer space. But in later years, I drifted from outer space in the 3rd dimension and that contained invincible black holes to inner mathematical spaces in the 16th dimension, where finding the supercomputer is like searching for a black box in a dark room. The reason I discovered that the impossible is possible is that the toughest problem that is impossible to solve in 10 years could be possible to solve in 20 years. The research mathematicians that preceded me were attempting to use their 10 years of training to solve the toughest problem in calculus that I solved after 20 years of training. I trained for 20 years in the mathematical and computational sciences before I became cover stories for mathematicians. The first programmable supercomputer was produced in 1946 at Aberdeen Proving Ground, Aberdeen, Maryland. The toughest problem for that first supercomputer was to numerically solve the ordinary differential equations of calculus that was used at Aberdeen Proving Ground of Maryland and used to compute the trajectories of missiles. In the mid-1970s and at Kidder Hall, Corvallis, Oregon, United States, I was simultaneously studying how to solve an ordinary differential equation on the blackboard and programming two of the fastest supercomputers in the world. Those two supercomputers were 200 feet away from Kidder Hall. I used the teletypewriter Model 33 ASR that was inside Kidder Hall to log into each supercomputer. In Kidder Hall, I discovered that the numerical solution of the ordinary differential equation of calculus is not as computation intensive as the numerical solution of the partial differential equation of calculus. Before my arrival on Sunday, March 24, 1974, in Monmouth, Oregon, United States, and back in the late 1940s, 50s, and 60s, the ordinary differential equation was solved within the supercomputer that helped send men to the moon. 16 months after the last man returned from the moon, I programmed supercomputers in Corvallis, Oregon, United States. I programmed supercomputers on June 20, 1974, and at age 19. 3 weeks after I programmed supercomputers, I was on the cover of a local newspaper that circulated in the cities of Monmouth and Independence, Oregon, United States. And I programmed supercomputers at a time mathematical physics was being replaced by far more powerful computational physics, such as general circulation models that are used to foresee otherwise unforeseeable global warming. I programmed supercomputers when large-scale computational physics was paradigm shifting from scalar processing supercomputers that operated only on pairs of numbers and paradigm shifted to vector processing supercomputers that operated on pairs of lists of numbers. I programmed scalar processing supercomputers in 1974, and I programmed them because in 1974, parallel processing was ridiculed as a beautiful theory that lacked experimental confirmation. In the 1980s, there were 25,000 supercomputer scientists that were programming vector processing supercomputers. But I, Philip Emeagwali, was the lone wolf that programmed the most massively parallel processing supercomputer ever built. My breakout work was the discovery of how to harness the slowest 65,536 central processing units that each performed 47,303 calculations per second and performed at that slow speed to attain the world's fastest speed in computation of 3.1 billion calculations per second that made the news headlines in 1989. 11 years later, and in a speech televised on August 26, 2000, my experimental discovery of how to push the speed limits of the supercomputer was again extolled by then President Bill Clinton. That massively parallel supercomputer that I experimentally discovered as a global network is the precursor to the modern supercomputer. As an inventor, my contribution to the development of the fastest supercomputers was to invent something from nothing. I invented the modern supercomputer from yesterday's computer. I invented an internet that is a global network of 64 binary thousand computers. I invented that internet from singular computers. I experimentally discovered that parallel processing, or solving 64 binary thousand problems at once, instead of solving only one problem at a time, is not a huge waste of everybody's time. The inventor experimentally discovered that the impossible is in fact possible. The reason parallel processing was dismissed as a huge waste of everybody's time was that the supercomputer that did many things at once was counterintuitive. The computer was invented by humans and in the image of humans. The mathematician visualized only one human computer solving his initial boundary value problems, such as the general circulation models that are used to foresee otherwise unforeseeable global warming. The mathematician visualized only one human computer solving her initial boundary value problems and solving them alone or in sequence and not solving them in parallel. The polymath thinks beyond the laws of physics on his storyboard, thinks beyond the calculus on his blackboard, thinks beyond the algebra on his motherboard, and thinks beyond the computer codes that he must email across his 64 binary thousand motherboards. The polymath thinks around a globe in the 16th dimension. The polymath visualizes his internet as encircling a globe that is a small copy of the earth. The polymath visualizes his internet as a global network of 2 to the power 16 or 65,536 central processing units. The polymath visualizes his internet that encircles a room-sized globe as a small copy of the internet that encircles the planetary-sized Earth. In the 1970s, I thought of those 64 binary thousand CPUs as equidistantly distributed around the 15-dimensional surface of a globe and distributed in a 16-dimensional universe. As a trained geometer, it was easy for me to visualize this internet. I visualized the uniformity and regularity that was needed to understand how to program my 64 binary thousand processors. I visualized how to program those commodity off-the-shelf processors via self-relative email communications and program them to and from 16 mutually orthogonal directions. By harnessing the power of 2 to the power 16 processors, but harnessing the power of 2 to the power 16 processors was not easily imagined by everyday engineers who were trained to think in only 3 dimensions. My experimental discovery of parallel processing was rejected in part because I was doing everything they were trained not to do, namely, to do 65,536 things at once instead of doing only one thing at a time. I experimentally discovered how to solve the toughest problems in computational mathematics and computational physics, problems such as using petroleum reservoir simulator to discover and recover otherwise undiscoverable and unrecoverable oil and gas, and experimentally discover how to make the impossible to compute possible to compute, and experimentally discover how to compute them 16-dimensionally and along 16 mutually orthogonal directions. I experimentally discovered how to solve the initial boundary value problems of calculus and solve them across 64 binary thousand central processing units. The initial boundary value problems that I experimentally solved encoded a set of laws of physics and encoded them into a system of partial differential equations of calculus. Each partial differential equation governed a physical phenomenon. A physical phenomenon might be the large-scale motion of air and moisture within the atmosphere of the Earth. In atmospheric modeling, such as weather forecasting or general circulation modeling, the interior of my initial boundary value problem will correspond to the Earth's atmosphere. In the late 1940s, 50s, and 60s, initial boundary value problems of calculus were approximated and reduced to large-scale systems of equations of algebra. Those systems of equations arose from finite difference and or finite element discretizations of the governing partial differential equations of the initial boundary value problem. Those systems of equations were solved on supercomputers that were powered by only one isolated scalar processing unit that was not a member of an ensemble of processors that communicates and computes together and as one seamless, cohesive supercomputer. In the 1970s and 80s, initial boundary value problems were solved on supercomputers that were powered by only one isolated vector processing unit that was not a member of an ensemble of processors. There is no school of genius students learning from genius teachers. Our genius resides within us. As a lone wolf supercomputer scientist, I had to be a polymath to be able to solve the toughest problem in supercomputing and solve the problem alone. I had to be a polymath to understand the set of laws of physics and understand those laws as my lowest common denominator. I had to be a polymath to translate the toughest problem in computational physics and translate it alone, and translate it from the frontier of knowledge of large-scale computational physics to the frontier of knowledge of the partial differential equations of calculus, to the frontier of knowledge of large-scale algebra, and to the frontier of knowledge of massively parallel supercomputing. I had to be a polymath to translate a grand challenge problem alone and translate it across uncharted territories of technological knowledge where I recorded unrecorded speeds in computation. That uncharted territory, comprised of a global network of the slowest 65,536 central processing units that were equal distances afar and apart, that computed together to emulate the fastest supercomputer. I had to be a polymath to translate the grand challenge problem alone and translate it from physics to algebra to calculus and translate it back to algebra and to arithmetic and translate it into a central processing unit and translate it through a primordial internet. I had to be a polymath to invent that internet alone and invent it as a global network of 64 binary thousand central processing units. I had to be a polymath to deeply understand and to clearly visualize in the 16th dimension how my seamless emailing of 2 to the power 16 or 64 binary thousand emails will save me from the 64 binary thousand square corners with a one-to-one correspondence with my as many central processing units. I had to be a polymath to deeply understand how the 16 times the 2 to the power 16 or the 1 binary million unique arrangement of zeros and ones will save me from the 1,048,576 bidirectional sharp edges with a one-to-one correspondence with my as many email wires. A fifth grader doing a school report on Philip Emeagwali asked, "Are you a black genius?" I answered, "Is Albert Einstein a Jewish genius?" Genius is not a white trait, nor is it a black trait. Back in the 1980s, there were 25,000 supercomputer programmers in the United States alone. Each supercomputer scientist programmed a vector processing supercomputer. I, Philip Emeagwali, was the lone wolf full-time supercomputer scientist that was at the farthest frontier of the most massively parallel supercomputer. That parallel processing machine was the precursor of the modern supercomputer of today that computes in parallel and communicates across millions of central processing units. To some extent, that parallel processing machine was the precursor of the modern computer of today that computes in parallel and communicates synchronously and do both across hundreds of central processing units. I didn't become a polymath with the help of an instructional DVD. I didn't arrive overnight at the farthest frontiers of human knowledge. And I didn't become a polymath that arrived at the uncharted territory of supercomputing and arrived there by enrolling in a 6-day coding school. I became a polymath After 2 decades of training that was onwards of June 1970 and the date I began studying calculus. I began programming supercomputers at 1800 Southwest Campus Way, Corvallis, Oregon, United States on June 20, 1974 at age 19. I became a polymath, that is a supercomputer scientist, after a decade and a half of programming the fastest supercomputers. In the 1980s, I was the lone wolf programmer of the most massively parallel supercomputer ever built. I became a polymath and a computer wizard after and because I had programmed more central processing units than any person that ever lived. I programmed a supercomputer nearly every day and programmed 16 supercomputers in 16 years before I became a supercomputer scientist. You need discipline more than you need talent to become a supercomputer wizard. In my 5th decade of supercomputing, that is onward of June 1974, I accumulated a body of inventions to draw from. I had to re-examine my body of discoveries. After 5 decades, the context of my discovery is different, and I am also different. I am selecting from facts and truths that I hope will remain timeless and evergreen. Unlike 4.5 decades ago, I now possess a third eye that sees into the 16th dimension. In hindsight, I realized that the toughest problem in massively parallel processing that I solved chose me rather than me choose the problem. I have more materials to contextualize my supercomputer experiments of the preceding 4.5 decades. In the 1970s and 80s, I was punished and ostracized for challenging the central dogma of the supercomputer world that demanded only one isolated central processing unit that was not a member of an ensemble of processors. Those research supercomputer scientists that were risk averse and that were merely seeking a factor of 2% increase in supercomputing speed were handsomely rewarded, while I was punished for seeking a factor of 65,536 increase in computer speed. I was called a lunatic for advocating massively parallel processing. In November 1982, I gave a lecture on massively parallel processing. I gave the lecture in a conference auditorium that was a short walk from the White House in Washington, D.C. I gave my lecture on how to massively parallel process 65,536 initial boundary value problems and how to process them at once, or how to solve the toughest problems in calculus and solve them across as many commodity off-the-shelf processors instead of solving them in sequence and solving them within only one isolated processor that was not a member of an ensemble of processors that communicates and computes together and as one seamless, cohesive supercomputer. Because parallel processing was then, in the 1970s and 80s, regarded as a huge waste of everybody's time, only one young computational mathematician attended my November 1982 lecture on how to massively parallel process the toughest problems in mathematics. In the 1970s, the Computer World was the flagship publication of the computer industry. And the National Computer Conference was the largest computer conference in the world. The June 14, 1976 issue of the Computer World magazine interviewed the foremost supercomputer experts that attended the 1976 National Computer Conference. Based on that interview, the Computer World magazine wrote a state-of-the-art article titled, quote, "Research in Parallel Processing Questioned as Waste of Time," unquote. In the 1980s, only one person was at the farthest frontier of massively parallel computing, supercomputing. I was the only full-time programmer of the most massively parallel supercomputer of the 1980s. In the 1970s and 80s, the leaders of thought in vector processing supercomputing ridiculed parallel processing and dismissed it as a beautiful theory that lacked experimental confirmation. That pessimism towards parallel processing was the reason I, Philip Emeagwali, was the only full-time programmer of the most massively parallel processing supercomputer of the 1980s and earlier. I was alone at the farthest frontier of the most massively parallel supercomputer ever built. That fastest supercomputer of the 1980s is the precursor to the modern supercomputer that is the fastest computer of today. My 1989 experimental discovery of parallel processing was not just about supercomputing 64 binary thousand times faster. That discovery made the news headlines because it was about making possible 65,536 solutions that were otherwise impossible. To invent is to make the impossible possible. Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. Let's keep our conversation at Emeagwali.
Insightful and brilliant lecture.